Okay, so do you have any questions? Did you check the homework questions? Do you have an idea how to solve them? Questions? Are you sure? Okay, so let's continue from yesterday. If you remember what we had done, we were looking at this spin system. We are ignoring the kinetic energy, we are only taking the interaction of its spin and angular momentum with the magnetic field. So we first treated it classically, it's the system of non-interacting particles. So the partition function of the whole system, whether we treat it quantum mechanically or classically, will be just the nth power of the single partition function. So if we calculate Q1, in our case, it's just, we don't have this n factorial term, it's just Q1 to the power n. So it's enough for us to calculate the single particle partition function. And classically, this was the energy minus mu dot b. And so if you just put it in the partition function, if you remember, the partition function is nothing but the sum over the microstates of e to the power minus beta e. And this is just the microstates in this case just corresponds to different orientations of the magnetic dipole moment of my system. And so it's e to the power minus beta times this is the energy value. So the sum over different orientations is nothing but integration over both theta and phi over all the solid angle. And at the end of the day, this is the partition function we had obtained. And once we have the single particle partition function, the rest is kind of straightforward. We can obtain the n spin partition function by just taking the nth power. We have the Helmholtz free energy. Once we have the Helmholtz free energy, we can calculate the entropy and the internal, once we know the entropy, the internal energy of the system is nothing but the Helmholtz free energy plus Ts. And so basically, we know everything. The magnetization will be just the derivative with respect to B. So this is the magnetization. This turned out to be the internal energy. Then we looked at certain limits, how the system behaves at certain extremes. One extreme that we will be interested in will be high temperatures, and the other extreme will be the zero temperatures. But once we look at this expression, we see that the general behavior is determined by this parameter x, which was nothing but the ratio of mu b to the thermal energy, kT. So small x basically corresponds to large temperature or large magnetic field, small external field. So in this limit, what we would expect is that, okay, it's just the spins will be randomly moving, their orientation will be changing constantly. Of course, the magnetic field is trying to align it in a particular direction, but the thermal motion is just trying to randomize its orientation. If the magnetic field is not strong enough, or if the temperature is high enough, we would expect all orientation to be equally probable. And when we calculate the energy, for example, the energy tends to zero. That is what we expected, because you see, if the orientations are random, the energy is the probability of the energy of a single spin to be positive is the same as its probability to be negative. So the average would just be zero. We can look at how it goes to zero, and we see that it has this 1 over T dependence. And this is what's called the Curie law. The Curie law basically states that not the energy, but the magnetization, sorry. We did the same treatment for magnetization, and the magnetization just goes as B times 1 over T. And remember, the magnetization of a system is just the magnetic susceptibility times the applied field. So that's how we define the magnetization. And so in this system, the susceptibility is inversely proportional to the temperature. That is some result that we obtained from this statistical treatment. Well, the other extreme was the large X behavior, that is when T goes to zero. Well, in this limit, you see there are these two effects. One is the thermal motion, which tries to randomize the microstates, the orientations in this case. The other one is the magnetic field, which tries to align the magnetic field. Now, in this extreme, the effect of the magnetic field is dominant over the effects of thermal motion, and hence we would expect a complete magnetization. And that is what we had actually seen. Then we looked at the other case, the same system, but this time we treated quantum mechanically. So as in quantum mechanics, the main difference will be in classical physics, the magnetic dipole moment can be oriented in every direction. But in quantum mechanics, the operator corresponding to the magnetic field, magnetic dipole moment, is given by the spin and the angular momentum. And the spin and the angular momentum cannot have arbitrary orientation, so they have to be oriented in particular directions. So that would be the difference in the quantum mechanical treatment. So the first thing we did was we studied how the magnetic dipole moment is related to the angular momentum operator. If you consider the electrons in an atom, the spins of the electrons in an atom, okay, they have spin. So classically, you can just think of them as small spheres rotating around themselves. Don't say this in a quantum mechanics course, but classically that's the description. And they also rotate around the nucleus. So both of them will contribute to the magnetic dipole moment. And the rotation around the nucleus is just some proportionality constant times the angular momentum, orbital angular momentum. When we look at the spin, this relation doesn't really hold for the spin. The contribution to the magnetic dipole moment to the spin for an electron is very close to 2, the proportionality constant. It's not exactly 2, but very close to 2. So the magnetic dipole moment of an electron orbiting the nucleus in an atom is proportional to its angular momentum plus twice its spin. Well, of course, now this is a much more complicated problem to solve for the energy eigenstates. So we have these electrons in the atom, they are orbiting. So the eigenstates to a lowest order would be eigenstates of J squared. The eigenstates without this magnetic field will be the eigenstates of J squared, Jz, L squared, and S squared. Due to the spin-orbit coupling, they won't be eigenstates of, let's say, Sz. But the first order in perturbation theory, we can just treat this as a perturbation, and then the energy eigenvalues at first order do not really change. The energy modification of the shift in the energy is just the expectation value of this new additional term in the interaction in the unperturbed eigenstates. So we just did all the treatment, and we just found out that this is the, okay, where is the expression? So we have, it's in a sense similar to the classical case. The energies is proportional to some magnetic moment. In this case, it will be mu b times j, mu b times g times j, let's say. It is proportional to the cosine of theta. Well, in this case, the cosine of theta is just m over j, m being the z component of the spin, and then b. So it's essentially similar to the classical expression with some modifications due to the quantum nature of the problem. And so the possible values of the third component of the spin, m, just goes from minus j to j. So you just sum up, and we just end up having the Q1, the single spin partition function. Well, there is a slight difference between the notation in your book and the notation I just used in the class. In the book, this x times j is defined as x. So in the classical limit, it does go to the classical x. So once we have this partition function, then the rest is kind of straightforward derivation. That is what we will do today. What is the energy? What is the entropy? What is the specific heat? What are are there some qualitative differences between the classical and quantum treatments, etc. And one thing we did was, okay, so we have the quantum picture. There's also the correspondence principle. I mean, if you have a quantum system, which if it has a classical limit, then the quantum results should go to the classical results. Now, in this case, the main difference between the classical treatment and quantum mechanical treatment was that the orientation of this spin or the magnetic dipole moment is not continuous, only there are discrete values. But there is a limit that we can study in which it becomes continuous. That is when j goes to infinity. Well, of course, on one hand, we want j to go to infinity so that m over j takes continuous values. You see, m over j is cosine theta. So m over j takes continuous values, means that the spin can be oriented in any direction, the magnetic dipole moment. But on the other hand, we don't want the shift in the energy to diverge. You see, when j goes to infinity, m also goes to infinity. If we don't do anything else, then the energy shifts for some states, goes to infinity, which is not the classical result. The quantum mechanical energy just takes values from minus infinity to infinity. That's also not something we want. So what we do is we also set g to 0. So we set j to infinity so that the orientation of the magnetic dipole moment will be infinite, this j. But at the same time, we set g to 0. And so that the shifts in the energy, the maximum shift in the energy, is still finite. There was a slight confusion. You see, in this expression over here, if you just set j to infinity, g just becomes 3 over 2. But keep in mind that j is restricted between L minus n and L plus s. So s is limited. So if you want to take j to infinity, L should also go to infinity in such a way that g should go to 0. That is our requirement for the classical limit. Then, okay, so we just looked at the partition function. We just have seen that, okay, in the classical limit, it just becomes this partition function. This is what the quantum mechanical partition function becomes. This is what the classical partition function was. So if you just compare these two, they are basically the same. So we do recover the classical limit. Now let's look at the other properties. You see, this is our partition function. So some of the questions we would like to ask: what is S? For example, one thing we would expect that S should satisfy is that at t equal to 0, S should go to 0. That is the thermodynamics third theorem. Also, on physical grounds, we expect S to go to 0. You see, at t equal to 0, there is no thermal motion randomizing the orientations of the spins. So the only influence on the spins is the magnetic field, and magnetic field will align them in the same direction. So there is a single orientation and single microstate, and the logarithm of 1 is just, which should be the entropy, is just 0. That is what we also expect here. Now S was minus derivative of the Helmholtz free energy with respect to the temperature. If you don't mind, let me just change the notation so that I will be consistent with the book. So I will just call x before j times x before is x now. So this over here just becomes x, and this is x over j. And now x is not this one, but this one. Times j. Okay, so that is, remember, in the classical limit we kept g times j to be finite. And, well, nothing else changes. So here we have j. Just a change of notation. So this is minus the derivative with respect to the temperature, remember, A was minus kT, logarithm of q1, which is a k times derivative with respect to temperature of T times logarithm of q1 let's take the derivative. This is k times the logarithm of q1 plus kt times 1 over q1 times the derivative of q1 with respect to t. So this is our q1. Well, q1 depends on t only through x. So x was just mu b, the Bohr magneton, g times j times b times 1 over kt. This is our x. And that is the only temperature dependence in q1. So we can write this as k times logarithm of q1 plus kt times 1 over q1 times the derivative of q1 with respect to x times the derivative of x with respect to t. Well, this is k times logarithm of q1 is the logarithm of twice sine hyperbolic x divided by e to power x over j minus 1 plus kt over twice sine hyperbolic x times e to power x over j minus 1. This is 1 over q1. Well, the derivative of this q1 with respect to x will be, twice cosine hyperbolic x divided by e to power x over j minus 1 minus twice sine hyperbolic x divided by e to power x over j minus 1 squared times the derivative of this denominator, which is 1 over j e to power x over j. Times del x over del t. Del x over del t is just minus x over t. Let us try to convert everything in terms of x. So let's see, we might be able to simplify it a bit maybe. So this is, well, let me try to write it in a slightly different form. You see, twice sine hyperbolic x divided by e to the power x over j minus 1. This was just e to the power x minus e to the power minus x divided by e to the power x over j minus 1. So this is e to the power x minus e to the power minus x divided by e to the power x over 2j minus e to the power minus x over 2j times e to the power x over 2j. Well, it's not simpler. Okay, so nothing to do. Let's try to simplify it a bit. So this is k times the logarithm of twice sine hyperbolic x divided by e to the power x over j minus 1. Well, here this t is cancelled by this t over here, Now this factor cancels one of these exponential terms over there, and these two are cancelled by this one. So what remains is plus k over sine hyperbolic x times cosine hyperbolic x minus sine hyperbolic x over j 1 minus e to power minus x over j multiplied with minus x. This is the entropy of the system. So the first, our expectation, what is the entropy at large temperatures? At t goes to 0 means t goes to infinity means x goes to 0. So s becomes k logarithm of sine hyperbolic of x is as x goes to 0. You say this is 1 plus x minus 1 minus x over 2. So this goes to, this cancels this one. This just makes a plus 2 over here, 2, so it's just x. So you see, if you come back over here, this is just x. In the denominator, you have e to power x over j minus 1, that is one plus x over j minus 1. This is typically x over j. Now let us also calculate cosine hyperbolic x. And this is 1.
I think we made a minus sign mistake.
Where?
I'm not sure, but just go above. This cosine hyperbolic x should get a minus sign, I guess.
Well, let's see, it's over here, it's this term over here. So that is the derivative of q1, which is the argument of the logarithm.
No, it's okay. When we were copying this line, like
this line here.
You said we had a minus overall. There should be minus sign.
No.
And then cosine hyperbolic x should be plus, so there should be minus sign.
No, you see, if you look at over here, I cancel e to the power x over j minus 1 with this factor. Inside, what remains is cosine hyperbolic x with a plus sign.
Yes.
But there is this overall minus sign,
Oh.
which I move over here. This is the overall minus sign.
Okay. Then the
second term is sine hyperbolic y.
Because you changed the sign of the 1 and the e to the sign.
No, you see, here we have e to the power x over j minus 1 multiplied with this factor over there. So basically, I just moved it to the denominator. So that is why here there is also a minus sign over there. And okay, so we also have one more term, 1 minus e to the power minus x over j is approximately 1 minus x over j. This is also x over j. So now we can calculate the entropy. So this is what I need. Now, this is the entropy. at t goes to infinity, well, it has k logarithm of twice sine hyperbolic of x, this is twice x, divided by e to power x over j minus 1. Well, that is x over j. So x times j. This is the first term. Minus kx sine hyperbolic x, we just said that that is approximately x. Here we have 1 minus sine hyperbolic x is again x over j. Okay, 1 minus that term is x over j. So this is approximately what the entropy is at t goes to infinity, and this is equal to, well, let's say these x's cancel, these ones also cancel, these ones cancel, the j's cancel. So this is basically 0. We have k times logarithm of 2j. Okay, as usual, we should always ask, does this make sense? You see, this is not the t goes to 0 limit. So it doesn't need to go to 0. This is the t goes to infinity limit for a single particle. Well, for a single spin, we already said that as t goes to infinity, the thermal motion basically dominates any effect of the magnetic field. So all the possible microstates are equally probable for my single spin. How many microstates does it have?
2j plus 1.
2j plus 1. So we are missing a plus 1 somewhere. So we are almost there, let's say, but there is a plus 1 that we are missing somewhere. Well, it might be either in the limits that we are missing a plus 1, or in Q1 we are missing a plus 1. Well, let's check our limits first. You see that 2j is basically from here to here. Let's e to power, this limit is correct. There is no j dependence anyway. So then we have the x to e to the power x over j minus 1. Well, there is no problem also over here. Now when we substitute over here, well, there is no logarithm from this term. So there cannot be any correction from here. So our expression seems to be wrong. And I know where it is wrong. Let's go back to our derivation of yesterday. When we were calculating Q1, when we were doing that summation, here, this is where we made the mistake. We are not subtracting all the ones from j equal to m is equal to j. M is equal to j term should remain. So
j plus 1.
we are summing, the second term is from m is equal to j plus 1. So that is our mistake. So let me use a different color. So this is j plus 1 over here. Well, here, what I can do is I can write this as, let's see. Let me just factor out e to power x over 2. What will remain will be e to the power minus j plus 1 over 2 of x minus e to the power j plus 1 over 2 of x divided by 1 minus e to the power x. So the correction would be, the 2 is correct. Here we don't have j, but j plus 1 over 2. And in the denominator we have basically e to the power minus x over 2 minus e to the power x over 2. So Q1, now let me just rewrite it. Sine hyperbolic x times j plus 1 over 2 divided by sine hyperbolic x over 2. This is our Q1, corrected one. Well, in this treatment of the classical limit, nothing should really change, because basically what we did was this factor 1 minus x should go to 1 minus e to the power x should go to x. Now in the numerator we have sine hyperbolic of x, which does go to x also. So nothing changes here. The classical limit still holds, so I will not correct it. So let us just go to today's lecture. So this is our corrected partition function. Okay, so we have to do all the derivatives, etc. Again, so entropy. Now let me just copy it. Yeah, this result is still correct. This doesn't depend on the explicit form of the Q1. This is k times logarithm of sine hyperbolic x times j plus 1 over 2 divided by sine hyperbolic x over 2 plus kt times, well, let me just write it below, sine hyperbolic x over 2 divided by sine hyperbolic x times j plus 1 over 2. If I take the derivative with respect to x, well, just sine hyperbolic becomes cosine hyperbolic, and cosine hyperbolic becomes sine hyperbolic. So it's just j plus 1 over 2 times cosine hyperbolic x times j plus 1 over 2 divided by sine hyperbolic x over 2 minus sine hyperbolic x times j plus 1 over 2 divided by sine hyperbolic squared x over 2 times 1 over 2 multiply all of this by minus x and divide by t. Basically that is the derivative of x with respect to t.
By the way, do we need to change our x?
Oh, you are right. So instead of x everywhere, I will write now x over j. So this is 1 plus 1 over 2j. This is here we have 2j. Now everything should be correct. So S is k times logarithm of sine hyperbolic x times 1 plus 2j, 1 plus 1 over 2j, divided by sine hyperbolic x over 2j. So here the t's will cancel, so we have minus xk sine hyperbolic x over 2j divided by sine hyperbolic x times 1 plus 1 over 2j. Okay, hold on, let me just make a cancellation. This sine hyperbolic will cancel this one and one of this one. So this is not there. 1. Inside we have 1 plus 1 over 2j cosine hyperbolic x times 1 plus 1 over 2j and minus, okay, this sine hyperbolics. Okay, so this is our S. Now let's check the small x limit. So S now becomes k times the logarithm of, well, you see, we already said that sine hyperbolic of x just becomes x in the small x limit, so this is logarithm of x 1 plus 1 over 2j divided by x over 2j minus k times x 1 over x times 1 plus 1 over 2j. Inside we have 1 plus 1 over 2j. Well, cosine hyperbolic just becomes 1 when its argument is very small, minus x times 1 plus 1 over 2j divided by x over 2j multiplied by 2j. Well, as in the previous case, this 2j is cancelled by this one, this x cancels this one, so all this parenthesis just becomes 0. And in this large T limit, large temperatures, the entropy is approximately given by k times, well, here these cancels, k times logarithm of 2j plus 1. Okay, now we have the answer that we would have expected from physical grounds. So there's high temperature, the influence of the magnetic field is negligible, so the only thing is the effects, thermal vibration, thermal fluctuations, let's say, which says that all microstates should be equally probable. So there are 2j plus 1 states the system can be in. If there are 2j plus 1 states, then the entropy is logarithm of 2j plus 1 times k. So this is what we expected and what we obtained. Now let's look at the small temperature limit. This is our, no, that's not x. The corrected one is here. So this time x goes to infinity. And you see sine of x times alpha, sine hyperbolic of x times alpha in this limit just goes to e to the power x times alpha over 2, assuming alpha is positive. Cosine hyperbolic, again it goes to e to the power x alpha over 2 in this limit. And basically those are the things that we will be needing. So S is, if you look at the above expression over here, well, there's this first term, this is the logarithm of e to the power x times 1 plus 1 over 2j divided by e to the power x over 2j. This is the logarithm. minus x times k 1 over e to the power x times 1 plus 1 over 2j. Now there is a factor 2 times 1 plus 1 over 2j. Cosine hyperbolic is e to the power x 1 plus 1 over 2j divided by 2 minus e to the power x 1 plus 1 over 2j. This is the sine hyperbolic in the numerator divided by 4j e to the power x over 2j. So let's see, this will cancel this one. So the first term is just x times k. Minus, well, let's see over here, this term cancels this one and this one. Minus, and this 2 will cancel this 2, and here we will have 2. Minus xk times 1 plus 1 over 2j minus e to the power minus x over 2j divided by 2j.
Why there was a 4 over there?
Well, because here we have a factor 2j. Secondly, sine hyperbolic has that additional 1 over 2, this 2. Both sine hyperbolic and cosine hyperbolic has in their definition that 1 over 2. So that makes it a 4.
But we also have again 1 over 2 factor in the numerator and denominator.
Here, you mean here there is this 1 over 2, additional 1 over 2.
No.
Where? So in this cosine hyperbolic we have this 1 over 2.
Yes.
Oh, you mean in the sine hyperbolic also we have, you are correct. So this is,
It should be only 2.
it's just 2, and which is completely cancelled. So you see this one cancels this one. So that's kind of nice because we expected the entropy to go to 0, but we are looking at the limit that x becomes infinitely large. So now entropy became x times k. Let me also take out the j times e to the power minus x over 2j. This one minus, we have 1 over 2j. Yes, 1 over 2.
Somehow it should be 1 over 2j.
Now you see there is this 1 over 2j over here, j over here. I'm taking the j out. Well, you see, it shouldn't be there.
Okay.
Now, why we are looking at the limit that x goes to infinity? When x goes to infinity, the exponent goes to 0. So that is fine, but not that 1 over 2. So this time though, probably we have done some mistake in the limiting itself, in the limit procedure itself. So let's see. This sine hyperbolic and cosine hyperbolic, I would say is correct. So S becomes k times, okay, there's no problem over there. So here we have minus x times k. Do we have an x? Yes, we have the derivative of x with respect to t. That x should be there. We have twice over this exponent, fine. 1 plus 2j is fine. In the cosine hyperbolic, we have this exponent over 2. That is fine. So we have minus, in the sine hyperbolic, we have this exponent. And from the numerator we have this exponent. Both have that 1 over 2 factor, so there's no factors of 2, so it's just 2. So there's just this 2j over here. So now when we take the limit, let's say when we did the cancellations, okay, so this cancels this x over 1 over 2j term. What remains is x times k. The logarithm of e to power x is just x, so here we have an x times k from the first term. Now in the second term, okay, we have this e to power x 1 plus 2j. Basically this sine hyperbolic cancels this cosine hyperbolic and also this sine hyperbolic. All of them are cancelled. So what remains is 1 over 2j minus e to power minus x over 2j from this one times 2j. So these exponents are cancelled. The 2 cancels these 2 over here. So we have xk minus xk, this 1 plus 2j from this one, minus this 2 is cancelled, minus j. And so we are looking at the limit x goes to infinity. Now let's see. S becomes, oh no, when x goes to infinity, no, we expect it to be 0. So there's apparently no problem over here. So let's see if we took the derivatives correctly. K times logarithm of q1. q1 is this one, fine. Mine plus kt times 1 over q1. This is kt times 1 over q1 is sine hyperbolic x over 2j divided by sine hyperbolic x times 1 plus 1 over 2j. This is 1 over q1. Derivative of q1 with respect to x will be the derivative of the denominator, numerator 1 plus 1 over 2j times sine hyperbolic becomes cosine hyperbolic divided by this one minus the numerator remains the, oh okay, now I see our mistake. You see here there is an additional term. The derivative of 1 over sine hyperbolic also contains a cosine hyperbolic x over 2j. That is the term that we ignored, we missed. So here I have an additional cosine hyperbolic x over 2j here. So here cosine hyper, okay, so in this term we have a additional cosine, from cosine hyperbolic we have e to the power x over 2j times 1 over 2. So there is a additional 2 over here, and this term is absent. It's just 0.
There's a limit of it goes to infinity over 0. Infinity times 0, sorry.
It's
just 0. It's completely 0. You see, we are not actually, you see, x goes to 0, but all those terms are cancelled. This one is cancelled by this one, and this term is cancelled by this term, completely.
limits that x goes to infinity.
Well, you say, just look at this as a Taylor expansion. In 1 over x, let's say. Or Taylor expansion in e to the power minus x. So the first term is 0. Of course, there are other terms which will not be 0. But so, at least what we expected turns out to be correct. Let's calculate the energy. What is the energy of this system? Any questions on this one, by the way? Any questions on this one? Well, you see, S, what we had obtained was S is equal to minus A over T. This is the first term. And the second term, well, let me write it in a slightly better way. Is minus xk 1 plus 1 over 2j cosine hyperbolic x times 1 plus 1 over 2j. And the second term is minus 1 over 2j is cosine hyperbolic x over 2j. No, not cosine, it's cotangent. So this is the entropy expression we have. But you see, the entropy of the internal energy is just A plus Ts. So here we have the S. Basically, if you just move this term to the other side, you get T times A over T plus S. And so this is equal to minus xkt 1 plus 1 over 2j cotangent hyperbolic x times 1 plus 1 over 2j minus 1 over 2j cotangent hyperbolic x over 2j. This is the total energy of the system. And keep in mind that x was the Bohr magneton G times J times B times over KT. So the internal energy of my system actually turns out to be mu B G times J times B 1 over 2j times cotangent hyperbolic x over 2j minus 1 plus 1 over 2j times cotangent hyperbolic x times 1 plus 1 over 2j. Now, one of the important physical properties of any system will be their specific heats. So let's just calculate the specific heat of this system also. Well, there is no volume, so the specific heat, basically the change in the internal energy with respect to the temperature. There is no work done on the system. So any heat given to the system will be equal to the change in its internal energy. And the specific heat is defined as the heat given per temperature change. Now, heat given is equal to the change in the internal energy, so we can easily write this derivative. Well, this will be equal to, again, this is du by dx. Well, the temperature dependence is only through the x over here and x over here. There's no other temperature dependence. So it's du by dx times derivative of x with respect to t, which is minus x over t. This is equal to, now let me not take the derivative. You can take the derivative. Well, the important thing about this one will be the internal energy. We already calculated the low temperature, we didn't calculate the low temperature limit of the, let's calculate the low temperature and high temperature limits. Small x and large x limits, let's say. So that will be enough for my claim. U, let's say as t goes to infinity. Well, as t goes to infinity, x goes to 0. And so if we expand it around x equal to 0, cotangent hyperbolic, remember it's cosine over sine hyperbolic. Cosine hyperbolic goes to 1. Sine hyperbolic at small values of its argument just goes to its whatever the value of the argument is. So it's Born magnitude JB 1 over 2j. Cotangent hyperbolic is 1 over x over 2j. Okay, we will need the next term. Minus 1 plus 1 over 2j. 1 over x times 1 plus 1 over 2j. This cancels this one. This cancels this one. So this is just 0. Okay, this plus, of course, there will be terms of the order of x squared. So if you want to see how u goes to 0 at large temperatures, we have to calculate the next term. What is the next term in this expansion? Let's say cotangent hyperbolic alpha. When alpha goes to 0, that expansion we need. So this is e to power alpha plus e to power minus alpha divided by e to power alpha minus e to power minus alpha. So this is 1 plus alpha squared over 2 plus 1 minus alpha plus alpha squared over 2 divided by the same things with a minus sign. Well, these alphas will cancel in the denominator. 1 plus, just the other way around. Plus alpha and minus alpha will cancel in the numerator. Here, 1 and alpha squares over 2 will cancel in the denominator. So this just brings a factor 2 over here. This term brings a factor 2 over here. 2's will also cancel. So this is 1 over alpha plus alpha over 2. This is what the cotangent hyperbolic is. So U is in the large temperature limit is mu b g j b 1 over 2j. Well, here we have 1 over alpha is 2j over x plus x over 2j minus 1 plus 1 over 2j times 1 over x times 1 plus 1 over 2j plus x times 1 plus 1 over 2j again this the first terms will just cancel each other. B G J B 1 over 2j times x over 2j minus 1 plus 1 over 2j squared times x. Well, the important thing will be for me will be gjb 1 over 2j squared minus 1 over 1 plus 1 over 2j squared multiplied with x. This is u. If you write down the specific heat, which was du by dt, this is du by dx multiplied with dx by dt, it goes to 0. T goes to infinity. Well, du by dx is just a constant, but dx by dt is proportional to x over t, which goes to 0. This just goes to 0 at large temperature, the specific heat. Well, we already know that at T equal to 0, specific heat should also go to 0 from thermodynamics. Remember the third law of thermodynamics. So as T goes to 0, specific heat goes to 0 because the entropy goes to 0. So how does the specific heat behave? So basically, it starts from 0. And eventually it should go to 0. So it should have such a behavior. Somewhere it will be non-zero. So this is what's called the Schottky anomaly. So basically, at small, low temperatures, the specific heat has a maximum, has a local maximum. Well, in this case, we don't have the thermal motion of the particles. So if you add the thermal motion, the specific heat still doesn't go to 0 at large temperature. At large temperature, if you just take the ideal gas law, it's just some constant at large temperature, the specific heat. It should go to some constant at large temperature, but at low temperature, still there is this local peak, which should be seen due to the spin degrees of freedom of the system. This is what's called the Schottky anomaly. So basically what's happening is at low temperature, there's only the ground state. If you increase the temperature, if you start increasing the temperature, there are all other possible available states to the system. So basically the energy just increases very fast initially. Then it keeps on increasing but slowly. And since it's just a derivative, so that's why we see this maximum in these spin systems at low temperature. Any questions? Now let's get one more thing. Okay, this is the specific heat. Well, this is the internal energy of the system. For a single particle, keep in mind. This is valid for a single particle system. And what we had seen is the average energy of the system So what we know, the energy of the system, at large temperatures, it goes to 0. Well, at small temperatures, This should be the temperature. Well, you see all of them are in the ground state. The ground state has this energy. So at 0 temperature, it has some finite negative value. And then at t goes to 0, it increases. And at t goes to infinity, it becomes 0. This is how U changes as a function of temperature. If we look at the entropy of the system, at t equal to 0, the entropy starts from 0. And as we increase the entropy goes to some limiting value. And this limiting value was k times logarithm of 2j. Now let's go for a simple case, so that we will be able to. What we will be trying to do is, you see, U eventually goes to 0. But you see, if you just take one of these spins, the spin can be aligned with the magnetic field, then its energy will be negative, or it can be anti-align with the external field, in which case its energy will be positive. So in principle, the spin of every system, the energy of each spin can be both negative and positive. But in these cases, the only regions we could obtain will be positive, negative energies. There is no configuration, at least here, which tells me which has a positive U. But keep in mind, you see, we are always talking about positive temperatures. If we would allow negative temperatures, you see, this is U. Well, negative temperatures just corresponds to x being negative. If x is negative, cotangent hyperbolic becomes negative. So U changes sign. So a better plot of U as a function of temperature would be, well, at t equal to 0, U has some energy, some finite negative energy. Then as we increase the temperature, it increases and then saturates at 0. At t goes to infinity, it is 0. Well, if t goes to infinity or minus infinity, doesn't really make any difference. But if you allow negative temperatures as t goes to 0 from the negative side, this time it should go to plus infinity. So you see, we do have positive energies. Okay, so we had we have the limit of U. You see, this is what U is. And negative temperature just changes the sign of x. So so it's just negative temperatures will be just a symmetrical limit of this one, basically, because it just changes the sign of U. If you look at the entropy, we had the expression of the entropy somewhere. So what does the entropy do? As we go to, if we take negative temperatures. Well, again, to obtain some analytical results, let's just try to look at a case J is equal to 1/2. This will be a simpler case. So we will have some analytical solutions. Now, what I would like to do is I would like to express, let's say, S and U maybe in terms of themselves, or maybe express the temperature and the entropy in terms of U, so that we can look at what happens in the whole possible range of U. Let's start with Q1. In this case, Q1 is just sine hyperbolic x times 1 plus 1 over 1 divided by sine hyperbolic of x over 2 times 1 over 2.
It's a given function. So can't we say that as t goes to minus infinity, it will just behave like as we did in the positive temperature?
Q1, yes.
So the same thing goes for the entropy.
The entropy will eventually go to zero though at infinite temperatures, or at negative temperatures also. At negative infinity, it will also go to zero. So let's say this is sine hyperbolic 2x divided by sine hyperbolic x. This is our Q1. Can we simplify it further? Not really. A minus kt logarithm of Q1 logarithm of sine hyperbolic 2x minus logarithm of sine hyperbolic x. S will be minus a over t, this is the derivative of the first one, plus kt times the derivative of the logarithm with respect to x will be cosine hyperbolic 2x divided by sine hyperbolic 2x multiplied with 2 minus cosine hyperbolic x divided by sine hyperbolic x times minus x over t. U is just kt, t's cancel, minus k times x twice cosine hyperbolic 2x divided by sine hyperbolic 2x minus cosine hyperbolic x divided by sine hyperbolic x. Now, the first thing I would like to do is what is temperature as a function of U. That is what I would like to solve. And of course, this just means I would like to express x as a function of U. Let me cheat. I mean, let's not do all the derivations, etc. In the book, there is already the result. So this is the Schottky anomaly. So, okay, this is the entropy as a function of U. Now, this will be what is critical for us, the entropy as a function of U. Now, you see, what happens over here, this is the plot of the entropy as a function of U. You see, the energy of the system, if you look at the energy of the system, there is a minimum possible value when all the magnetic dipole moments are aligned in the direction of the magnetic field. So that's a single state. So in this state, the entropy is 0. U has its minimum value. Then there's the other state in which they are completely randomly oriented, all the magnetic dipole moments. So that is the state that corresponds to U is equal to E. U is equal to 0, the average U is equal to 0. That is when the temperature goes to infinity. So this is the state basically in which the entropy would be maximum, because there are many ways. When U is equal to 0, half of them should be aligned in the direction, half of them should be aligned in the opposite direction. If you just count the number of ways that energy can be distributed, that is the maximum. So the entropy is maximum. If you increase U further, there should be more, let's say, if when U becomes positive, there should be more spins aligned in one direction than the other one. But that would basically mean that the number of possible microstates corresponding to these will be smaller. So entropy starts to get smaller and smaller. Basically, U larger than 0 is, mathematically speaking, exactly equal to the U less than 0, just to flip the spins. So up to U is equal to 0, entropy increases. So when you keep increasing U from above 0, the entropy decreases. And hence, so basically, if you just solve them, the entropy S in terms of U, this is U is equal to 0. When everything is in the ground state, T equal to 0, entropy is 0. Then it starts increasing, and then it starts decreasing again. This corresponds to U is equal to mu B times G times J times B. Of course, for the case J is equal to 1/2, L is equal to 0. And this corresponds to U is equal to minus mu B times G times JB, evaluated at J is equal to 1/2, L is equal to 0, S is equal to 1/2. So this is how the entropy changes as a function of U. And the entropy goes to 0 because there is the maximum possible energy to the system. And when the system has that maximum possible energy, there is a single microstate corresponding to that. And remember that 1 over T is just ds over du. So you see here at this point, derivative is infinite, it is increasing infinitely fast at t equal to 0, at u is equal to 0. So 1 over t is infinite, so this point corresponds to t is equal to 0. And then let's say at this point, entropy increases as a function of u. So at that point, t is larger than 0. And you see the derivative of s with respect to u is decreasing. It starts from infinite value over here, and then here at this point, the derivative of entropy with respect to u is 0. So if the derivative with respect to u is 0, 1 over t is 0, that corresponds to t becomes plus infinity. So we started from t is equal to 0. As we increase the temperature, or the internal energy, let's say, then eventually when u is equal to 0, t is equal to plus infinity. But we can still increase u, because there's no limit on u, so we can keep on increasing. Well, the limit is not 0 at least. We can keep increasing, but if we keep increasing u, the entropy starts decreasing. So ds over du basically becomes negative. Well, that means just slightly to the right of that point, u is equal to 0, and here on the right hand side, t is actually minus infinite, because 1 over t is negative 0, almost 0, let's say, minus infinitesimal number. So t is minus infinite. At this point, entropy is decreasing, the derivative is negative, So temperature is negative. And this point is again corresponds to t is equal to 0 because the derivative is infinite.
But it goes from the left.
Hmm?
It goes, when t goes to 0 from the left.
From by taking negative values. So basically, do negative temperatures exist? Yes, in such a system. But they are not colder than 0. They are just hotter than infinity. So because you see, the negative temperature states are basically have more energy. So if you just connect a negative temperature state to a positive temperature state, energy will flow from negative temperatures to positive temperatures. That's also something that we had shown when we were discussing thermodynamics. There we said that if negative temperatures exist, then to increase the entropy of the system, to be consistent with the second law of the system, heat should flow from negative temperatures to positive temperatures. Well, basically, as in this example, negative temperatures have more energy. So that's why it goes to the regions which has less energy. Of course, the problem is, can we create such systems? Or is it just hypothetical?
I think we can.
Yeah, we can. You see, basically the idea is, for this system, we should have a system which has an upper bound of energy. Spin systems is such an example. But the problem with spin systems, with any particle with spin, it doesn't only have energy corresponding to its spin, it also has energy corresponding to its kinetic energy, to its motion. So the total energy of an object with spin is not bounded from above. So it's infinite, so it cannot have negative temperatures. But you see, if you have systems, for example, the nuclear spins are such systems. Okay, on one hand we have interactions of spins, or thermal equilibration of the spin. Let's say the relaxation time for the spin degrees of freedom. So how long does it take for the spin degrees of freedom to have a thermal equilibrium, to have a distribution corresponding to thermal equilibrium? The other thing is, how long does it take for the spin degrees of freedom and the translational kinetic degrees of freedom, let's say, to have a thermal equilibrium? So there are two relaxation times, two times it takes to reach equilibrium. If the relaxation time among the spins is much, much smaller than the relaxation between spins and kinetic degrees of freedom, that is, for short time intervals, we can just ignore the thermal degrees of freedom because they are not coupling with the spin degrees of freedom for a short time. And nuclear spins have this property. They don't interact with the translational degrees of freedom much. The relaxation time is much longer. And for such systems, what you do is, you take this system, put it in a large magnetic field, wait for a long time. Well, long compared to the relaxation times. So we have a system which is relaxed. And let's say it's at small temperature, not negative temperature, but small temperature. So that it will be almost completely magnetized. Then you can just reverse the magnetic field. If you reverse the magnetic field, in that case the spin will stay in that way for a long time. But that is a system with negative temperatures. Not this one. And okay, so this is some experimental result. So basically this region is the region. Well, I mean, you can find the article on the internet. I did find the article. There are not much details, but what I understood is basically what is meant by deflection is just it's a measure of the magnetization of the system. So you take your system, put it in a coil, and through the coil you send some alternating current. So and then see in which direction the system just rotates. So basically, it's a magnetized system. You put it in a coil with a changing magnetic field, So of course, in a magnetic field, the deflection of this magnetized system will depend on its magnetization. So you see, in this region, its magnetization is in the opposite direction of the magnetic field, and it stays so for, let's say, a long time. In this case, let's say 2 minutes. For 2 minutes, the relaxation time of the spins, let's say, with the thermal vibrational degrees of freedom, kinetic degrees of freedom, is of the order of, at least in this case, it seems 2 minutes. So for up to 2 minutes, it stays in a negative temperature state.
Is this the same thing that we're doing in magnetic resonance imaging?
In MR, I'm not really sure.
I thought that they are doing the same thing. I don't know.
Well, I don't really know the detail, but what my understanding is that what they do is they look at the radiation emitted by spin flips.
Mm-hmm.
So when nuclear spins flip, they emit some radiation. They can detect that radiation. And of course, they put the person in a strong magnetic field, and for some time, let's say several minutes at least, it's not really in thermal equilibrium. To reach thermal equilibrium, some of the nuclear spins should flip, so that eventually they get an equilibrium spin distribution. And during these flips, they should emit some energy. And since they don't really interact with the kinetic degrees of freedom, they cannot really transfer that energy to translational degrees of freedom. And the easiest way would be to emit some photons. Mm-hmm. And that's what I think what they measure.
I guess every atom has different energy value when they change, when they are aligning their spins, and it gives a characteristic idea about which atom we have in that object. I think that's how they are measuring what we have in our, let's say, legs and hands.
I'm not sure if they are giving you any chemicals in NMR.
No, they are not giving any chemicals, but they understand what do we have inside.
Mm-hmm. Well, the nuclear, you see, here we have the magnetic dipole moment. So when the spin flips, the amount of energy released will be determined by the magnetic moments. Mm-hmm. Different atoms have different nuclei have different magnetic moments. So looking at those magnetic moments, well, you see the hydrogen and oxygen and carbon, they each have different magnetic moments. And I don't know if NMR should be looking at the nuclear magnetic moments. As I said, I don't really know the details, but my guess. So let's just end here. That's all I would like to discuss about these magnetic systems. So next week we will be starting the grand canonical ensemble. We also allow the number of particles change, not just the energy. Any questions?
For its spin 1/2 particle, just assume we have only one particle, and let's say U is 0, which means that particle could be in a spin up state or spin down with equal probabilities, right? So in that case, we have 2 microstates, right?
Yes.
But we are sure that the particle is not in a specific state, right?
Well, you see, okay.
If it is, then it should have minus U or plus U.
Okay, so there are certain subtleties in are you referring to quantum
Yeah, only quantum.
Okay. So you see, the thing is, if you look at a single, what we are doing over here is we are saying that I don't know anything about the particle. That's my initial assumption. And then I say that, okay, I measure the average energy of that particle and so I say that it is 0. Then I can say that, okay, it's either spin up or spin down. And is it in a definite state? Well, you see, these concepts don't really make too much sense when you are talking about a single particle. Okay, we are looking in this problem, we are looking at a single particle, because since we have n non-interacting particles, if we know the average energy of one spin, then just multiply it by n to obtain the spin of all of them, energy of all the system. So in that case, in that sense, here we are still talking about single particles, but we don't know what it does. So that's basically the initial assumption. In the canonical ensemble, we are saying that I don't know anything about the particle except its average energy. Then what are the probabilities that it is in one or the other one? Well, of course, the problem becomes a bit more involved when we have quantum mechanical systems. You see, in quantum mechanical systems, it doesn't have to be in one energy eigenstate or the other energy eigenstate, but it can be in a superposition of them. How do we take those superpositions into account? Do we need to take those superpositions into account? How do we do all this treatment in quantum mechanical systems? Completely quantum mechanical. Up to here, the only quantum mechanical ingredient we have is actually the discrete energy levels and the discrete microstates. We didn't really use anything else. But it does become, I mean, we will be discussing them later on. In that case, we will be defining some operator, some other matrix, so-called the density matrix, which will characterize the thermal properties. And then we will say that, just like using the Liouville's theorem, etc., there we said that the density of states in phase space, in classical statistics, we could define that density of states in phase space. And we had seen that it depends only on the energy. And the same, more or less the same arguments done in a density matrix in quantum mechanics basically leads to the same conclusion. So there is a density matrix which characterizes the statistics of the system. It can take into account possible superpositions and the probabilities at the same time. And then this density matrix should be a function of the Hamiltonian operator. And in fact, it should have the same form, that it should be e to the power minus the Hamiltonian operator over kT. And then in an energy eigenbasis, it is diagonal. And basically there are no superpositions in energy eigenbasis, because any superposition shows itself in the density matrix as off-diagonal elements. So basically what's happening over there is, even if you create one particle in some superposition, let's say, that's not a thermal equilibrium configuration. The system, due to interaction, eventually reaches a thermal equilibrium. And this thermal equilibrium basically destroys all superposition. Of course, the energy eigenstates are still superpositions of some other states, but all superpositions of the energies, they just go to zero. Have you seen the density matrix in quantum mechanics? Here we had this rho, the density in phase space. In quantum mechanics, we also have rho called the density matrix as an operator. It's not a function of x and p. Other questions? So see you next week.